So your class of lipids is really just designated according to its solubility. Right? And their solubility tends to be relatively insoluble in water. You do get some solubility to it, and it's that kind of balance between insoluble and soluble that really classifies and is the main characteristic of your lipids. Right? That, if we want to get all fancy on it, is reference to amphipathic, meaning they're both water-soluble and insoluble. There's a variety of forms. You've got your open-chain forms, and then your cyclic forms. So we've got a bunch of different lists of all the possible, or not all the possible ones, but a lot of possible open-chain forms and a lot of the cyclic ones. We will talk about some of those open-chain forms, at least where they're coming from. And we'll mention that a lot of our hormones and cholesterol or steroids are coming from lipids as well. Synthesis of which is actually kind of neat and could be devoted on a whole separate class, but we won't get into the synthesis. Our primary category comes in as fatty acids. So we talked about, or I mentioned, this amphipathic nature of our lipids. What that's in reference to, so we take a look at these structures. Each of these have this red part and this blue part. Well, red typically references what element? Oxygen is actually typically red. And then usually black we leave as carbon. Right? In this case, blue is referencing our carbon. Okay? So if we look at each of these, they each have this similar kind of pattern. We've got this long section of pretty much just carbons and hydrogens, and then another section at the other end of primarily oxygens. Okay? Well, oxygen being one of our most electronegative elements will suck that electron density away from whatever it's attached to, and that starts to generate a very large partial negative charge, if not a formal negative charge, on one end of the structure. We now have an ionic compound. As we talked about way back at the beginning of the semester, as soon as you have an ionic compound, you have something that is now water-soluble. Okay? But we also have this massive blue section at the end, which is now just carbons and hydrogens. Those are all nonpolar covalent bonds, which means they have a net zero charge on each of those atoms. So we now have a very nonpolar section. Okay? It's the balance of the nonpolar and our polar that is really our characteristic for our lipids. Okay? That amphipathic situation. The polar group interacts with water. Our nonpolar group interacts with not water. So that, as far as our scientific terms, isn't fancy enough, so we end up calling these by different names. What would those different names be? Hydrophobic and hydrophilic. Okay, so those are your big characteristics. You get hydrophobic coming from your nonpolar section, and your polar section gets you your hydrophilic. Okay. Ultimately meaning water-loving and water-fearing. Okay. So kind of neat molecules in that respect because we have these kind of this dual nature to them. There is some sort of nomenclature that can come out of this, which we'll address in just a second here. The R group, if we're looking at our general fatty acid structure, actually, did I provide one? I didn't provide one, sorry. I have a feeling I had intended to. So we're looking at our oxygen bound out to an R. We're saying a fatty acid. We need to make sure we have the acid portion. So we have our fatty portion as our R group. Does fatty have two T's?
It does today.
Yes. It does today. That's good enough. And we have our acid portion over here. Okay, so there's our fatty acid. Within the nomenclature of these, we want some kind of shorthand, because going through and naming some of these could be a bit tedious because there's a lot of carbons in there. You have to count them all out, go by the dodec, tridec, all that fun stuff that you may remember from organic. So instead, we get this kind of pseudo-notation or pseudo-shorthand, which is written right here. Okay? The number of carbons and the number of pi bonds. So if we take a look at, apparently I advanced the slide, this bottom example, we could go through and count our carbons. We go 1, 2, 3, 4, get the idea, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Was that 15? 16. So we have 16 carbons in this fatty acid, so we could refer to this as a 16. And then our colon, what comes after the colon is the number of pi bonds within the fatty acid, okay, or within the fatty portion. How many pi bonds are within the fatty portion for this molecule? 0. So we could refer to it as a 16, 0. Okay. If we moved to, say, this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We now have an 18 carbon fatty acid with how many pi bonds? 2 pi bonds. So we can call it an 18,2 fatty acid. Okay. So you may see that nomenclature pop up. You're referring to the number of carbons and the number of pi bonds. As I poked around a little bit more last night, I don't think it's addressed in your textbook, but we can add a little bit more information to this. It's nice that we know we have 2 pi bonds, but it might also be nice to know where those pi bonds are located. So that where reference is usually added with a delta, and I do not know the meaning of this. And then you'll see a number reference, multiple number references for each of those pi bonds. So for the example we've got here, oh man, I'm going to count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh man, 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like we got 9, 12. Okay. So all we're trying to do is reference where that pi bond is located. Okay. When we're looking at our fatty acids, depending on their location, ultimately where they're coming from, we give them a different name, which is a bit silly because they're ultimately representing the same thing. It's just a question of where the source came from. So in animal fats, or sorry, in fatty acids found in animals, we tend to refer to them as fats. Okay? In fatty acids that are found in plants, we refer to them as oils. Okay? And what this is ultimately coming down to is the saturated versus unsaturated difference. Okay? So if we have a saturated fatty acid, there are no double bonds. Every single carbon is fully saturated with hydrogens. If we have an unsaturated fatty acid, okay, some or one or more of those carbons, it usually comes out as 2 or more of those carbons, is missing hydrogen. So we have a double bond, okay? Double or triple bond officially. So why do we differentiate them between fats or animal fatty acids and plant fatty acids? Well, it has to do with their structures and the different phases associated with those fats. If we take a look at a fat from an animal, say like butter, versus a fat from, say, even a plant. You got margarine. Let's push it a little bit further. It's another good plant source of fatty acids. Olive oil. It's a bit silly just call it all oil. Let's call it olive oil. What is the marked difference in the physical properties between these? So yes, it is going to come back to saturated versus unsaturated, but let's take it further back to just the obvious difference. If I take butter and put it out on the table, we're looking at different phases. Animal fats tend to be solids, and plant fats tend to be liquids. Okay. So why do we see this phase difference? Okay, and this gets back to your point, saturated versus unsaturated. Solids, liquids. Okay, so then the question becomes, which is which? Which one is saturated, which one is unsaturated?
I would say animals is unsaturated.
Okay. So one possible option is we can look at the polarizability of our molecule. And if we're looking at our difference between those structures, we're talking about a pi bond versus sigma bonds. Okay? The pi bond has external electron clouds. That pi bond can now polarize better. Well, if it polarizes better, we're potentially going to increase intermolecular forces. So we might expect for our solids, because we have solids, we might expect that increased polarizability within the pi bond. So we might guess that our butter is going to be unsaturated, right? That's where you were going. Is that the result? Does anybody know?
I don't think so.
It's actually the opposite. Okay. So that seems a bit odd. Why is that the case? Because if we look at just the functional group and we think back to organic chemistry and those applications, we might think, hey, it's more polarizable. It should have a higher boiling point. Well, it turns out that your animal fats tend to be saturated and your plant fats tend to be unsaturated. Okay, so that goes counter to what we kind of think about when we think about organic chemistry and our intermolecular forces. Okay? But we're not looking at just that bond. We're not comparing an alkene to an alkane. We're comparing a structure that has an alkene in it as opposed to a structure that does not have an alkene in it. Okay? And the important part to that is if we take a look at our saturated structure, we have this very nice kind of up-down pattern all the way through. Which means if I'm going to put a second molecule there, I can probably fit it nice and neatly within that stack. I can start to fit a whole bunch of those nice and neatly within there, theoretically better than I just drew it, okay, where we get that nice kind of close packed interaction. What happens if we now look at our alkene, okay, our unsaturated one? We can get nice close packing until all of a sudden we got this weird kink in it that causes these things to not pack quite as nicely, particularly if, say, I rotated the molecule, and instead of the double bond being in that cis up, it's in the cis down direction. What happened to the amount of interaction out here? It's decreased. So as we unsaturate our fatty acids, we start to now make it more difficult to pack these molecules next to each other. Right? There's more space between them. What happens if you increase the space between molecules? You're moving from solids to liquids to gases. That's ultimately what's happening here. So our odd kind of comparison of thinking strictly on the functional groups has to move beyond just our raw functional groups into a molecular effect. How does that molecule affect its packing? And that's where we're getting saturated versus unsaturated. Is it just as simple as that? Not quite. Because we could potentially change the orientation of that double bond, cis versus trans, and that's going to change, again, how it packs. If we go into a cis conformation, that's going to put this massive little kink in it that's going to make it hard to stack. If we put it in the trans conformation, doesn't really change the zigzag pattern. So in a trans fatty acid, those are going to be almost equivalent to a saturated fat because of how that double bond forces the structure to align. So what we're looking at is how the double bond affects our overall structure and then the overall kind of packing. So it's not quite as simple as just looking at the alkene or even as simple as saying saturated versus unsaturated. We also have to take into consideration the conformation about the double bond, be it cis versus trans. Okay? So the general trend that we get out of this is that our saturated fats tend to have higher boiling points. Our unsaturated fats tend to have lower boiling points, which is why our unsaturated fats come out as liquids and our saturated fats come out as solids. Okay? So that's our primary difference within those. Questions? I think that's kind of neat. I nicely or not, I believe, covered up all the names. Whoops. Within these. Officially, you may encounter some of those names, so it's not a bad idea to review through the textbook and just see what kind of names pop up for your fatty acids. Okay. The next part of this is what do we do with these fatty acids? Okay, well, one option is we take it through and we decompose them down into energy. The other option is we now need some way to store them. Okay. So one of those common ways to store them is in waxes. Okay. So a lot of plants tend to do this. You find waxy skins and things like that. Okay, that waxy material is taking a fatty acid and changing its structure around a little bit. Okay, so we started at a fatty acid and we've now become what new functional group? So there's our fatty acid. So we got fatty. We sort of have acid, which I'll put in air quotes for the moment. What do we have out the other end? So another fatty section. Okay. So this is no longer a fatty acid, and it's not fatty acid fatty. Okay. You can come up with a better system here. What functional group is that in between? It's not an acid. It's an ester functional group. So what we can do is take advantage of the chemistry of the carboxylic acid, and we can convert it into an ester functionality. That ester functionality now changes the intermolecular forces. Okay. Would we expect our waxes to be soluble in water? No, they have one small polar section in that ester. Everything else is this big fatty section. Okay, and the fatty section is not going to interact with water. So by a simple manipulation of changing that functional group from an acid to an ester, I've now taken the compound that was potentially water soluble and turned it into something that is insoluble in water. Okay, so we can use wax to actually repel water, okay, or trap water on the inside, or allow it to move to some place where we want to collect water. Okay. Yeah. Really anything else I can add on that? Questions?
What beeswax has ester groups in it?
I don't know the specific composition of beeswax, but I would guess that what we're looking at is some kind of fatty acid wax process. Sometimes the nomenclature transitions nicely, sometimes it doesn't. Okay, so if we're calling it beeswax, it's probably correct.
I have a question.
Uh-huh.
On the fatty, the butter versus the oil,
Mm-hmm.
you said the butter has a higher boiling point, melting point?
It's going to have higher both.
'Cause
Yeah.
Is the boiling point for butter, isn't as high as some of the vegetable oils, corn oils? 'Cause that's what you use to fry.
Yes, but when you melt butter, I don't think you can turn it.
Butter will melt to a liquid.
Turns to a
Well
liquid,
before it boils.
and
But
then
boil.
does it boil? So it's
It
you're
actually
probably
is a
right.
flash point, isn't it? It actually doesn't even really boil, it's a flash point, doesn't it just burn?
There's the issue. So
Okay.
referring to it as a boiling point is not going to be a good option. You're correct in that. I should be referring to it as a melting point. Because are these actually going to turn into the gas phase? Most of them, no. What are they going to do instead? They're going to combust. They're going to decompose. They're going to react with oxygen. So you're right. Boiling point was a bad option. I should be saying melting point for all of these. In general, your trends for melting points versus boiling points are roughly the same, but we never hit the boiling point. We hit a decomposition point. Okay, so referring to the boiling point doesn't make any sense. Does that make sense?
Yes.
Thank you for asking. Another way that we can store these fatty acids is in triacyl glycerols. Okay? It's a fun thing to go through and say. So let's break down that name a little bit. Glycerol at the end of that is referencing the compound glycerol. Okay? Glycerol should look kind of familiar. Anybody come up with an idea of where glycerol potentially can come from?
Soaps.
It's in soaps, but it's also in all fatty acids. Where could we get the glycerol molecule to react with our fatty acid?
Where does it react with the hydroxyl group of acid? What is it, esterification?
No, you're trying to make it. I want you to make the glycerol. Does that look familiar?
Oh, glyceraldehyde?
Does that look familiar? Where did that molecule come from? Glycolysis? Okay. So we can potentially make glycerol from glycolysis. So we can make that central molecule, which can then potentially link out to your fatty acids. Okay. The glycerol molecule is potentially a byproduct of glycolysis. So if we had a ton of extra energy around, maybe we don't need to convert our glucose molecule all the way through the electron transport chain. So what we can do is convert it to our glyceraldehyde and the DAP potentially, and then convert that, reduce that molecule into glycerol. Once it's in glycerol, then we can use that as our storage mechanism for picking up our fatty acids. Okay. So that's kind of where our glycerol is coming from in the natural source. Okay. We're one step away from it when we talk about glycolysis. What can we do now with the glycerol molecule? Okay. Well, we have a nucleophilic oxygen, okay, in the glycerol molecule. In fact, we have 3 nucleophilic oxygens. Those nucleophilic oxygens can attack an electrophilic carbon. So here's our nucleophilic oxygen. Where's our electrophilic carbon? The carbon of our fatty acid. And an enzyme will help facilitate that nucleophilic attack and ultimately then the elimination of this group. Okay. So we would eliminate OH. That's a horrible leaving group. What could we do to potentially help that out? The other piece that's coming out of here is H+. Okay. Hydrogen ion, which can meet up with or facilitate making that hydroxide a better leaving group. So when we go through and do our condensation reaction of our fatty acid with our glycerol, it's referred to as a condensation because one of the products that we see out of it happens to be water. Okay? So we end up pushing across to our water as a side product. If we were actually going to balance this equation, how could we balance it? We need 3 fatty acids with 1 glycerol to go through and make a single triacyl glycerol. What else? We need 3 waters as well. Okay. So it's looking at the big changes and how those changes can potentially occur. Back to our name, we had the glycerol group that's kind of connecting everything together. And then we have this tri for 3 groups. 1, 2, 3. What is the acyl referencing? That is technically your acyl. And here's your glycerol molecule. Okay, so there's our triacyl glycerol. So would we expect this molecule to store more or less energy than a wax? So our energy is found in those carbon-carbon bonds. Does this have more energy in it or less energy than a wax? Yes, we are making some approximations here. Which structure has more carbon-carbon bonds? How many R groups ends up in our fatty acid, or sorry, our triacyl glycerol? 3 R groups. How many R groups do we have in our wax? 2. Okay. Whoa, that was not supposed to happen that way. So we have 1, 2. Which one has more carbon-carbon bonds? Could potentially see the fatty acid having more carbon-carbon bonds, assuming all the R groups are the same length. Okay, so we do have to make that assumption there. These can be hydrolyzed. So if they're going to go through and be hydrolyzed, you're going to end up using an enzyme known as a lipase. Okay, lip for your lipid, and ace for cutting them open. And so what happens is the reverse reaction. The lipase catalyzes the cleavage of that bond by having water come in, kick that out, and we're back to the fatty acid. Now that we're in the fatty acid, we have a lot more functionality associated with it as opposed to being in the glycerol. Why would we have more activity in the fatty acid than in the glycerol and than in the triacyl glycerol?
Repeat that again.
Why would we have more activity, enzyme activity around fatty acids than we would around triacyl glycerol? It's more open.
Yeah, sterics.
Okay. There's a massive steric issue with the triacyl glycerols. We can potentially get at the acids on the outside, but the one on the inside is buried in there. Okay. Further the inside attack off of each of those fatty acids is also now blocked because the other group is there. Whereas when we move to the fatty acid itself, it's a little bit more accessible, a little bit more available, easier to break down. Okay? So when we're converting it up to our triacylglycerol, we're really planning on storage. We're just trying to get it out of the way so it doesn't decompose. Okay? Last way that we can go through and mess with our triacylglycerols is we can do saponification. Humanase. How many people have heard of the humanase enzyme? Probably haven't heard of it because I made it up. What does that mean? It's us. Okay? It's humans going through and actually converting our triacylglycerols over to our fatty acids. When do we typically do that? Fair enough. But when you're dead, it is actually going to be a biological enzyme that's cutting it down. Either what was already naturally in your body, or it's going to be some bacteria bringing in a lipase. Okay? So I'm not looking at a natural process, and we're looking at an unnatural process. The human is coming in and causing this to happen. When do we do that? Anybody wash their hands today?
No.
What'd you use? Soap. Fatty acids work as great soaps because they have a nonpolar tail and a hydrophilic head. Okay? So if we want to make soap, one of our possible options is to take our standard fatty acid, our triacylglycerol, and convert those back to the fatty acid. Now that we've got the fatty acid, we can use that as a soap molecule. Okay? That's where our saponification comes from, and apparently people can't spell when they spelled soap. Okay, was an appropriate response, I guess, to that one. So we can go through all sorts of other permutations of this. You can run into phospho-acylglycerols. Okay, as you might guess, what's changing about this? We're adding a phosphate group with our acyl and our glycerol. So our acyl is ultimately our fatty acid. The glycerol molecule is still the basic root, except one of the alcohols off of our glycerol is converted into a phosphate. Okay? How is that going to change the physical properties? Okay, as opposed to our triacylglycerol. So we go back, look at our triacylglycerol. What do we have out here? R groups, which were all,
Yeah, they're dying of oxygen, so it's more reactive.
these were all fatty. We do have more oxygens, but where are those oxygens located? In a fatty sandwich. Okay, so while we have increased the oxygens, we've equally increased, if not more so, increased the fatty part. So our triacylglycerides are really, really fatty in this process. Probably not very water soluble. Okay, so we've actually mitigated that water solubility. Is this something that we've seen in reality? What happens if you try to add butter to water? Okay, it doesn't mix very well. Okay, that's because what we're looking at is triacylglycerols in our butter. Okay, potentially. What happens when we move now up to the phosphoacylglycerol? We're still having our big fatty sections, but what else is brought in here? And in particular, a polar head group and a negatively charged oxygen. That ionic charge now makes that section very, very water soluble. Okay? So our phosphoacylglycerols increase our water solubility. We still got that fatty tail, but we now have some water solubility within this.
Is that how fire works, like emulsifier?
As I was preparing this, I saw a bunch of stuff on bile, and I was like, I should throw that in there because you already asked a question on bile, and I didn't throw it in there. I didn't even look up the structure, so I can't answer that. I will try and answer that question more appropriately on Thursday. We can run into something known as fingo lipids as the next possible option. Okay. You'll notice that we're looking at some similar version of our glycerol molecule, at least some sort of similar aspects to it, but we're seeing some also pretty major changes to it. we kind of still have our carbons with at least our electronegative side groups coming off of that, but we now also have this big long fatty acid chain coming off that as well. So we're now starting to change the basic character that holds all these fatty acids together. Okay, so of course we come up with a new name. This is where they came up with sphingolipids. And they're referencing the sphingosine, which is what they decided to name that compound. I have no idea where that came from. Okay. But that's what it's referencing. As we go through and put on fatty groups or put on fatty acids, we start changing the properties of this, and you get varying different names. So in aceramide, what you've done is taken your sphingosine and you've put on a single fatty acid onto the amine. Okay. If we go through and look at sphingomyelin, okay, you've got now a phosphate group and a whole bunch of other polar charge parts to this. You've got now yet another fatty acid in that middle as well. Okay, so all these are ultimately doing is alternate ways to store your fatty acids, but at the same time, we're really introducing this section. What is this important section that's getting highlighted? That is a very polar head group. So while we are now storing these fatty acids, we are also introducing this very polar aspect to it. Okay? So we aren't losing that polarity, which becomes important because where do we typically see lipids show up? In membranes, okay, which if I'm lucky is the next slide, but I have a feeling there's like 5 other of these possible things. Glycolipids. So again, you're taking your fatty acids and you're now stashing it in a slightly different formation. Okay, so it again gets a different name. Okay, why are they called glycolipids? We're bonding them to glucose. Okay, so we're including a carbohydrate in this. So we're usually looking at glucose or galactose molecules being tagged on into this. And then if we do gangliosides, we're now adding all sorts of multiple carbohydrate chains, for instance, potentially dealing with our ABO blood type functionalities. So our ultimate goal with all of the lipids is ultimately to get to a membrane. Okay? We have this duality associated with it, that hydrophilic head and that hydrophobic tail. Okay, so we've got a variety of ways that these can kind of self-assemble, which is kind of a neat word to go through and say, and it becomes a big buzz system. We've got self-assembling nanoparticles, which is officially true, but it's like that's called a cell. That's what it does. So what ends up happening is we take all of those fatty tails, and if we're in a solution that has enough of these, what those fatty groups are going to want to do is get away from anything that's hydrophilic or has water. Okay, so if we look at our standard biological solvent, that standard biological solvent is water. Okay, so our hydrophobic tails just orient themselves away from the water, and we put that hydrophilic end closer to the water. Okay, maximize that hydrogen bonding interaction and minimize that hydrophobic interaction. Okay, depending on how well or the different concentrations of each of these species, we can end up generating different structures. Okay? Biology does this exceptionally well on its own, and what they typically refer to it as is a bilayer sheet, okay, which is kind of an odd term. Why do we call it a bilayer sheet? Because our cells, flat structures that run on forever? No. So why are we calling it a bilayer sheet when we're talking about cells and not, say, something like a liposome or a micelle?
Because you actually have 2 sections, it's layered.
Okay, so number one, it can't be a micelle. Okay? In our micelles, the interior of the micelle is all hydrophobic. Okay? And we look at our cells, we have a hydrophilic part on the outside and we have a hydrophilic part on the inside. We got water across both places, that's where all the chemistry is occurring. So it absolutely does not work for biology to be a micelle. Okay, so that's a bad option because no hydrophilic inside. Why don't we refer to our cells as liposomes? Why do we still look at the cell membrane as a bilayer sheet and not a liposome? Said another way, what is the difference between a liposome and a membrane or a bilayer sheet? Kind of getting at a hollow core. A cell should have a hollow core though, right?
But it's the space, the amount of space.
It's the amount of space within a cell, okay, versus the amount of space within a liposome. A liposome is a cell for all intents and purposes. It has the exact same structure, except it is incredibly tiny relative to it. So if we look at both the inside and the surface of this, okay, we're going to see some curvature associated with those individual groups. If we look at a cell is now so largely round that if we look at any individual point on it, it appears to be a bilayer sheet. Okay. That's the reference, or that's kind of your key difference there, is just how big are those respective spaces. So a liposome is just a very, very tiny version of a cell. And liposomes have very particular characteristics as well. Okay. When we look at animals and plants, right, our plants, oddly enough, have a more fluid membrane. Why do they have a more fluid membrane? Well, what amino acids? What fatty acid was primarily making up your plant cells? The unsaturated fats, which cause little kinks and bends within that membrane surface, which then means it's necessarily going to be true that it's more fluid. Whereas in our animals, we have the saturated fats, necessarily makes it more static, which seems a bit odd. Okay? At least it does to me, because how much do plants move? I would have expected a more rigid membrane within a plant. Okay? But what's another difference that plants have that mammals don't, I guess?
Cell walls.
They have cell walls. Okay, so what we're talking about is the plant membrane, not the cell wall in this case. Okay? So we have a more fluid membrane in our plants, and it's more stiff within our animals. One of those contributing factors actually comes from cholesterol. Cholesterol kind of helps sit within there. It's a really odd-looking structure within the membrane, but it actually helps pack things a little bit better and more efficiently than just your standard fatty acids. I may have double-tapped. Should I double-tap? No. Right. Membrane composition. So what your textbook has done here is actually, I think, kind of a nice picture. We're taking a look at kind of a snapshot of a membrane or a cell membrane here. Which would we expect this one to match best? Liposome, micelle, or bilayer sheet? Why liposome? Okay, we're seeing it as a more round shape in this case. Okay, but they're doing that to help accent something else. What's that difference? What do you notice is different on the outside of this membrane versus the inside of the membrane? Right, it can be just the simple, obvious thing first, and we can worry about analyzing that further. Most of the inside is your phosphoacylglycerols, or what I was really fishing for was green, and the outside has a lot of these other colors popping up. Okay, so why does the outside have more colors and the inside not? Okay, well, that's going to go back to looking at each of those potential lipids. Right? And one of the trends that I started to notice is the lipids on the inside, our phosphoacylglycerols, happen to be smaller than the ones on the outside. Why might that be the case?
Because you only want certain things to go through. Only certain things should be colored or
I think it's going to be more relevant to the size of this. Okay. We're looking at a curvature associated with that. What's the curvature on the inside going to be? That's going to be very, very small. What we're going to need is to have lipids in there that can actually sit in that smaller space. Whereas if we look to the outside, we now actually have a larger space, a larger area. We can now fill that with larger polar groups. Okay. So it's just looking at the shape of how an individual sphere is created. So it's kind of a neat little observation. Okay. So we do see differences between the lipids, both on the outside of the membrane and on the inside. And some of it is probably more importantly due to what things need to pass through. Okay. So we're going to change kind of the permeability on the outside versus the inside. Because if we brought it to the inside, we probably want to keep it, on the inside. So we might make that inside surface more difficult to pass through. Okay? And again, it depends on what compound's going through it.
Let's say cerebromelain.
Cerebroside. Cerebroside? It's probably cerebroside, not cerebroside. Fluidity. So we just addressed this kind of fluidity option. As you have more unsaturated double bonds, that's going to necessarily cause your your individual lipid molecules to be more mobile within that membrane. Okay. As we add in more cholesterol, that cholesterol actually increases the interactions between the side groups. And it helps to keep that saturated tail nice and straight. The straighter that is, the better it interacts with the next one, which then makes that cell membrane or those lipids less mobile, more solid. Okay?
Which is what builds up on the inside of your arteries, right?
That one's debatable, so I'm not quite sure I want to open that can of worms. Cholesterol has been known to contribute to or be part of the cellular plaques or blood plaques. It's more an issue of part of than the contributing factor. Right? One of the analogies I just heard on that is that it's like calling the fireman the arson. Okay, the arsonist that started the fire. Every time you see a fire, there's a fireman. It's got to be the fireman's fault. Cholesterol is very likely actually helping to put out the fire. Okay, but it just happened to be the first thing that we noticed that was present. Okay. Still up for debate. They're still working on that. But
Kind of the eat eggs, don't eat eggs.
yes. Yep. Same issue there. So your model of membranes. If we look at an individual membrane within a cell, it's not just these lipids and that's it. Okay, remember, complex 2 was found within a membrane. So we have all sorts of proteins and potentially nucleic information stashed within these membranes. That's going to help facilitate the passage of things back and forth through the membrane. It's also going to change how that cell interacts with its outside environment. Because if we start to change the different sugar molecules on the outside, that can then have an immune response versus not an immune response. So when we're looking at our membranes, it's not just the lipids. There's a bunch of other stuff stashed within that. And so we end up getting this big sea of all sorts of different pieces hanging off of it. Common terms that you might see are integral versus peripheral. Integral meaning it's bound within the membrane itself. Peripheral, it's somewhere on the surface. You get transport and receptors. So as I'm fairly certain based on what I've been reading of your papers, we'll probably hear a lot about transport and receptors and how that's potentially occurring across those membranes. Okay, you get all sorts of signaling pathways. So if we encounter something on the outside, that may trigger something on the inside to say, hey, we need to go replicate because we're about to die. Okay? Something along those lines at least. The important aspect to note kind of within this is that we are looking at something that is kind of fluid. It's not just a solid and stationary and it doesn't move. These things are all constantly kind of moving and shifting through the membrane because we ultimately aren't changing the interactions all that much by shifting it through. So this was kind of a neat image that still gives me a little bit of a hard time to understand what they're doing. But what they went through to do to kind of test this fluid mosaic of looking at each of those individual pieces and how they interact with each other is they took cell membranes and they did this freeze fracture technique. So they froze a membrane and they broke it open and they could look at the individual surfaces. Right? So you can look at the inside of your bilayer and then you can look at the outside of your membrane. So you can see kind of all these little dots. All those little dots are coming from proteins that are now hanging out within that. So kind of a neat little technique. We can potentially figure out how proteins interact with each other or if they are near each other by tagging them with this molecule GFP. GFP stands for green fluorescent protein. Very, very common molecule used for a lot of biochem techniques. What it does is when it's near certain aspects, it changes its structure to the point that it now fluoresces. So you can then identify, is that GFP molecule near this other section. Right? As long as they have that proximity effect, you now get this fluorescence. If the proximity isn't there, you don't get the fluorescence. So you can use that as kind of a radio, or not a radio label, but a label within cells to see how things are functioning and what they're talking to or talking about. As far as your membrane transport, we've got two possible mechanisms. We've got passive versus active. We've already kind of talked about some of these. Passive, you're looking at driven with the concentration gradient. Okay? So we've seen this before. Where have we seen passive transport? Maybe it's easier to switch it up and look at the active. In the active, we're driving against the gradient. Where have we seen active transport? Sodium-potassium pump is a fair one to talk about, but we haven't talked about that yet in the class. Looking at the electron transport chain and ATP synthesis. What does the electron transport chain do? Electron transport chain doesn't make ATP. It transports hydrogens across the membrane to make a concentration gradient. Okay, so it is actually going against the gradient. Okay, that is active transport. The electron transport chain is active transport. You are actively moving hydrogen ions across that membrane at the same time you're transferring those electrons. Where is the passive transport occurring? Could look at oxygen diffusion as well. ATP synthesis is passive transport. It's the passive transport of the hydrogens across the membrane. We're taking advantage of that transport to form ATP through ATP synthesis, or in ATP synthase. There are other things that can factor into this. You get simple diffusion or facilitated diffusion. In facilitated diffusion, it's not technically active, though you are transporting the membrane across by transporting something, or transporting a molecule across, but the enzyme isn't intentionally dragging that molecule across. It's just getting transferred at the same time. Okay, so there are a lot of shuttles that we've talked about that kind of deal with your facilitated diffusion. Inactive, you're using ATP most commonly, but you could also potentially use NADH. In our secondary transport, we can potentially use a hydrogen gradient. There are lipid-soluble vitamins. So our vitamins, there's a whole bunch of them. These are all technically lipids because you've got all that non-polarity associated with them. Okay, we've got the big fatty section, and we have our polar hedge group. Okay. Vitamin E is kind of a neat molecule. It acts as a free radical scavenger. Okay. And that free radical scavenger is ultimately due to this functional group, which in its reaction is typically referred to as a quinone. Quinone. Okay, so it can do some kind of cool radical chemistry. So, exam questions, because I've already talked way longer than I wanted to do. Here we've got a couple exam questions as possibilities. Okay, so we'll keep the recording on this. Which of the following is not an example of a lipid? It says acid, though. Okay. D. Okay. Amino acids are not lipids. They're actually amino acids. There was a whole other section that we were talking about. Why is margarine more liquid than butter? So margarine, for those of you that didn't know, is actually a plant-based oil, synthetically designed to kind of give us that same sort of structure as butter. Okay. So it does come from plants, but does that explain why it's more liquid than butter? No. Okay. What we're looking at is those first two options that either being saturated or unsaturated. To make it more liquid, it needs to be more mobile. We're looking at a larger percentage of double bonds, so it's a larger percentage of unsaturation.
No, margarine is hydrogenated.
Partially hydrogenated, yes. So to go through and do, to make margarine, what they do is they take an oil from, I think it's palm oil usually, which has some double bonds within it. what they go through and do is they hydrogenate some of those double bonds, which now makes it more saturated, which then increases the melting point, okay, making it more like a plant, or sorry, an animal fat, which is saturated. Which of the following is not a characteristic of passive membrane transport? I do kind of apologize for this odd location of it.
Which C?
Oh, son of a. Let's make that a D.
Oh.
Okay. Not a characteristic of passive membrane transport. Your ETC was an active transport mechanism. Okay. On the exam, I will write that out as electron transport chain. I started to get tired writing this. I wanted to go home. Cholesterol is not found in which of the following?
Wouldn't know about cats.
Goats has always been a go-to answer for me, so I had to include that. Yeah, you're looking at avocados. You're looking at a plant. I had a biology teacher in high school who got really upset about that because during one of his biology classes as an undergraduate, his teacher had insisted that there was cholesterol in avocados. And he said, no, there isn't. He said, plants don't have cholesterol. And so the teacher said, well, let's ask the class. How many of you have heard that cholesterol is in avocados? And everybody raised their hands. It's like, of course they've heard that. You just told them that.
It has fat.
Yes, he's thinking of fats. Yeah. Sphingomyelin has a relatively larger polar head group than phosphoglycerol. Where would sphingomyelin be found in a small cell?
Okay.
The exterior face, the inside of the membrane, interior face, and the cytosol. We're looking on that exterior face of your membrane. Okay, because it's larger, we got a little bit more surface area on that outside. That's where we can slide that guy. Okay. Questions?
So